All right, today we are cracking open a cosmic cold case. The crime? A flagrant violation of the universe's most fundamental law, its ultimate speed limit. The prime suspect, you ask? A little theory called quantum mechanics. And the lead detective who first sounded the alarm was none other than Albert Einstein. So let's get into it.
Now, to really understand the crime, we first have to understand the law. And it all starts with a pretty simple question. Let's say the sun just poof, vanished right this second. How long would it take before we, here on Earth, felt the gravitational tug disappear and go flying off into deep space? The answer to that question reveals pretty much everything about how our universe is wired together.
You see, back in Isaac Newton's day, the answer would have been simple. Instantly. Gravity was this mysterious force that just reached across the cosmos in a single moment. But Einstein realized this whole action at a distance thing was a huge problem. It could lead to all sorts of paradoxes, like an effect happening before its cause. So he rewrote the rules. In Einstein's universe, gravity isn't a magical force. It's a ripple in the fabric of space-time itself. And nothing, not light, not gravity, nothing can travel faster than the speed of light. So we'd have a nice blissful 8 minutes before we even knew the sun was gone. This core idea, this cosmic speed limit, is called locality, and it's the bedrock of all modern physics. So with gravity all sorted out, it seemed like all of physics played by this local rule. But then, as Einstein was poking around in the bizarre new world of quantum mechanics, he found something that deeply troubled him. He had just discovered the first clue that this new theory might be breaking his most sacred law. And this gets right to the heart of quantum weirdness. Back in 1927, Einstein thought of this little experiment. Imagine you fire a single electron. Quantum mechanics says that before you look at it, it doesn't really have a location. It's what's called a wave function, kind of like a ghostly cloud of all the places it could be, all at once. But the instant you measure it, the moment it hits a detector screen, that whole cloud of possibilities just collapses. It snaps into a single, definite point. Okay, so what's the big deal? Well, the problem is how that collapse happens. It happens instantly, everywhere, at the same time. If that electron's probability cloud was a light year across, the moment you detect it here, the possibility of it being over there vanishes in that exact same instant. A measurement in one spot has an immediate effect somewhere else, faster than light could ever travel. And that, well, that was a direct violation of locality. Einstein, of course, had the perfect name for this. He called it spooky action at a distance. And he didn't mean that in a good way. To him, it was like a ghost in the machine, a sign that quantum theory had to be incomplete. There had to be something deeper going on, something more sensible and, local. This set the stage for one of the greatest scientific debates of all time, pitting Einstein against Niels Bohr, the champion of the new quantum theory. But for decades, pretty much the entire physics community sided with Bohr. Einstein's concerns about this spooky stuff were mostly brushed aside, and the case, for all intents and purposes, went cold. And this really shows you the two completely different worldviews at play. Einstein was basically saying, look, quantum mechanics is a fuzzy picture because it's incomplete. There must be some hidden variables, hidden information that locally determines everything. We just haven't found it yet. Bohr and his camp, on the other hand, had a very different take. They essentially said, stop asking what reality is really doing. The math works, it predicts our measurements, and that's all physics is supposed to do. So in 1935, Einstein and two colleagues came up with what they thought was the final knockout punch. It's called the EPR paradox. Imagine you create a pair of entangled particles. They're linked in a special way. If one has a property called spin up, the other must have spin down. Now, you send these two particles flying off in opposite directions, light years apart. The very instant you measure particle A and find its spin is up, you know with 100% certainty that particle B's spin is down. But how did particle B get the message? That information had to travel faster than light. For Einstein, this was it. Checkmate. This proved that spooky action was ridiculous, and that there had to be some hidden information carried by the particles all along. But here was the frustrating part. Both Einstein's local theory and Bohr's spooky theory predicted the exact same results in any experiment you could think of. And since you couldn't test the difference, the whole debate was shelved as philosophy, not real physics. The case file was closed. And there it sat, gathering dust for nearly 30 years. Until the 1960s, when a physicist named John Bell was rereading those old papers and had a complete aha moment. He realized this wasn't philosophy at all. It was something you could actually test. The investigation was officially back on. Bell's idea was pure genius. He came up with a clever twist on that EPR experiment. Instead of just measuring spin as up or down, he figured out a way to measure it along different angles. And this one simple change was the key. It created a scenario where Einstein's sensible local reality and Bohr's spooky quantum mechanics absolutely had to predict different outcomes. He had set a trap.
And here are the stakes, laid bare. Bell did the math and calculated that if reality is local the way Einstein believed, then when you run this new experiment, the measurements on the two particles should disagree with each other at least 33.3% of the time. But if quantum mechanics and its spooky connection are correct, the disagreement rate should be exactly 25%. There it was, clear as day, a mathematical line in the sand. Reality had to pick a side.
So all that was left to do was run the actual experiment. Starting in the 1970s and 80s, physicists like Alan Aspect finally built the equipment to perform these Bell tests. The entire physics world was on the edge of its seat. Was reality going to be local and sensible like Einstein hoped, or was it about to get really, really spooky? And the results came in, and they were just shocking and completely unambiguous. Experiment after experiment, getting more and more precise over the years, found the same thing. The disagreement rate wasn't 33.3% or more. It hovered right around 25%. Just as quantum mechanics predicted. Reality was spooky. So the verdict was in. The universe is non-local. Those faster-than-light influences, as weird as they sound, are a real feature of our world. You know, Einstein was absolutely right to be worried. He spotted a profound and deeply unsettling feature of quantum theory. He was just wrong about what it meant. Reality, it turns out, is even stranger than he could ever imagine. But hold on, because in this cosmic detective story, just when you think the case is closed, there is one final, absolutely mind-bending twist, a potential escape hatch that might just save locality from spooky action. But the price you have to pay for it is maybe the strangest idea in all of science. It's called the many worlds interpretation, and it gets around this whole problem of the wave function collapsing by proposing something truly radical. It just doesn't. Instead, when you measure that electrons spin, the universe itself splits into two. A new universe is created where you measured spin up, and another one is created where you measured spin down. Now, why on earth would you propose something so bizarre? Well, it has one huge advantage. If the wave function never collapses, there's no need for any spooky, faster-than-light signal between your two entangled particles. Both outcomes just happen, each in its own separate branch of reality. There's no spooky connection needed, and just like that, Einstein's beloved principle of locality is saved. And so this is where the investigation leaves us today, with two of the most bizarre options imaginable. Is our reality a single universe held together by mysterious instantaneous connections that defy our sense of space and time? Or is it an endlessly branching multiverse where every quantum event spawns countless parallel worlds and countless parallel versions of you? The case on locality might be closed, but the mystery of what reality actually is, well, that's still wide open.